first of all, about the key topics of discussion, I would kind of expect that all of the attendees have some exposure to machine learning and deep learning, because I won't be going through the basics of it from scratch. But if not, like, don't worry. Feel free to use the chat forum or reach out to me even after the session for any questions if you have. I'll try to answer to the best of my knowledge. But for this particular session, I'm going to mostly focus on using TensorJS and Node.js for training and inferencing of machine learning and deep learning models on client browsers and on edge devices. Okay. So along with TensorFlow.js, we'll take a look at TensorFlow Lite, which is a kind of a light optimized framework for the actual TensorFlow, where some of the models are kind of optimized enough so that like training, deployment can be done on lightweight edge devices like something like Raspberry Pi, NVIDIA Jetson, and so on. Apart from that, we'll take a look at something called TensorFlow Hub. So TensorFlow Hub is more like a repository of trained and registered models, which kind of people train on their systems using a lot of data. Then they try to register and version the trained models, and it can be reused by anyone else. And people can just directly use the trained model and deploy it on their edge devices. Okay. And finally, we'll see some use cases or case studies where real-time model training and inferencing can be done or is actually required for a lightweight edge device. And whatever we are kind of going to discuss will be actually be really applicable in those situations. Okay. So first of all, just to introduce everyone to the topic and why actually we are discussing this topic. So it is kind of estimated that by 2025, that there will be around 21 billion IoT devices in the entire world. Now, again, like I'm not going to cover about what exactly is IoT, and I'm hoping that everyone might have some exposure. But again, like if not, feel free to ask me. But typically, right now, the focus towards machine learning and deep learning is slowly going towards the edge deployment, where people are trying to use various AI algorithms on those edge IoT devices. And that's why there is a huge demand of such ML and DL applications, which can be deployed at edge or node devices. Okay. Now the question is, how do we actually perform the real-time machine learning on the edge? And before that, we are also going to see that whether it's actually necessary or not. Okay. So first of all, like, why MLDL at edge devices? So when we talk about edge devices or node devices, those are actually quite low powered, low compute resource devices, and it cannot handle the certain algorithms which are quite computationally expensive, which are kind of memory hungry. And typically, like whenever we talk about deep learning algorithms, right, when the data is huge, especially unstructured data in form of images or text or maybe speech signals, then doing any kind of computational operation on those edge devices is extremely difficult. Okay. And even let's say we have a trained model, the trained model itself in terms of size is huge. So even deployment in edge devices is quite difficult. And the other problem is, since the edge devices are kind of constrained with the memory or the computational power, doing real-time applications based on certain condition is extremely difficult. Okay. Say for example, when we are working for a manufacturing use case, and in the manufacturing plants, we would need to make an algorithm that can do anomaly detection based on the power consumption of some of the plants, or maybe some of the operational aspects of the plants. So and that would have to be deployed on the local systems. But if we really don't have that kind of capability, deploying such machine learning algorithms might not work at all. Okay. So basically, we might need to come up with ways or techniques to how to see whether whatever the current state of the art algorithms are there, can that also be deployed in local systems. Okay. And why at the edge again? As I said, sometimes some of these applications would need to be real time. So latency is something that is not acceptable for some of the use cases. So when I talk about latency, so in typical machine learning and deep learning use cases, most of the algorithms are run through an AI engine or a machine learning engine, that would be running on a remote cloud-based server. Okay. In most of the cases, people kind of try to pass whatever the data that they have in their systems, try to hit that remote server, get the predictions or the expected results which they are expecting, and then they try to do the rest of the remaining things. But in some of the real time use cases, that's actually a challenge, because the round trip time to the server can be quite high based on the amount of data, and even passing the amount of data is quite difficult if the volume and the the quantity of it is quite high. Okay. And also in some cases there are a lot of privacy related concerns, where it is expected that whatever the data that the machine is kind of capturing stays within that local environment, and it is not allowed to leave that device. So that's why that is also one of the valid reason why having this the facility of doing machine learning or deep learning at the edge is important. Other points would be like related to connectivity. So let's say some of the machines might not have direct connectivity to internet. So that's why the cloud-based machine learning or the AI engine might not be an option at all. And power consumption, as I said. So network connections are also quite power hungry. So some of the cases the devices are are meant to operate in low power mode. So that's why like it's kind of not uh, applicable to use something which can draw a lot of power because of the network connection, and to consume data or maybe establish a continuous connection with a remote server. Okay. So that these are the primary reasons I would say that why machine learning and deep learning at the edge is very important, and we are going to talk about how to do it also. But before that, as I brought a reference of the cloud-based, machine learning or deep learning workflow, this is how typically enterprise level MLDL workflow looks like, and this is how like most of the things are driven in a cloud-based remote server. And later we'll see that how the same architecture or the same flow can also be implemented at a local environment through edge devices and node servers. So when we talk about an enterprise level machine learning or deep learning workflow, we see that we have a data layer which would be providing the data, which would move to the analytics layer. So the analytics layer is where the actual algorithms run. So the algorithms would try to get the data from the data layer. It would try to apply, the algorithms and get the results. And once the results are obtained, it is kind of passed through a middleware API layer. So using the API, REST API interfaces, it can be integrated to any end application or any user interface layer, so that the users can actually consume the results of the entire workflow. Now, along with that, like most analytics layer has a or have a like monitoring and a feedback layer, because like sometimes we might need to do something like an incremental training or maybe a continuous training, as in when we get the live data, prepare a new version of the model. So that monitoring layer actually helps us to understand that the model which is deployed in production, how well it is kind of performing, or whether there are a lot of issues, or whatever the matrix that we use to kind of evaluate the model, how well it is kind of fitting that. And if let's say if it is kind of below an expected level of matrix score that we are expecting, then through the feedback layer it would trigger back again to the analytics layer, and it will tell that whether you need to kind of get more data to train, or maybe tune certain hyperparameters on real time, and so on. So this is how a typical cloud-based enterprise level machine learning and deep learning solution looks like. And the same can actually be implemented through a local system. And with this, we'll come to the next topic, which is like TensorFlow.js. And we'll see how TensorFlow.js, which is actually a kind of the same TensorFlow module, which can be implemented through JavaScript. And with the help of something like Node.js, the same kind of architecture that we saw over here can be implemented at a local based system. Okay. So TensorFlow.js is actually a library for machine learning in JavaScript, as I said. So most of us like who have worked, quite well in TensorFlow, or let's say any machine learning or deep learning related work, we kind of depend on Python, although there are other languages which are becoming more popular. But typically for web developers, JavaScript is kind of one of the go-to languages. So having TensorFlow.js or the flavor of TensorFlow in JavaScript made it actually very easy for some of the the cross-platform developers who can develop their own applications through TensorFlow.js. So along with TensorFlow.js, we can actually integrate it very well with Node.js, which is also another JavaScript-based cross-platform environment, framework. And with this, with going, both hand in hand, we can actually have a full machine learning workflow outside the cloud servers or the cloud-based environment into a more local edge-based environment. Okay, and that is mostly possible because I would say of Node.js, which can run as a local server and implement the same client server based model. And then TensorFlow can be used to either train or maybe retrain or maybe do the deployment part in direct local edge devices. Uh, Now, when we talk about the entire training and the workflow part, basically there are two types of machine learning and deep learning workflow that we usually do. In most of the cases, it is done through something called an offline workflow. So when I talk about offline workflow, the model training happens outside the real-time environment where we kind of get a lot of data from many places. We kind of do the required amount of processing, cleaning, then building the model, hyperparameter tuning. And once we have the trained model, then usually it is deployed on a real live production-based system. And then on real-time, live flowing data, we kind of get the specific results out of it. Now, the thing is, that is kind of the offline modeling workflow. And there are use cases, as I said, which requires, instead of an offline workflow, something which is much more real time and which requires an online training and inferencing workflow. Okay, so when I talk about online training and inferencing workflow, I mean that the training itself happens on real time, as in when we get live flowing data, and like based on the the training that gets completed, then it kind of deploys and gives you the immediate results. So initially we talked about that anomaly detection workflow in manufacturing plants, right? That is actually one of the good examples where we can actually say that online training and inferencing workflow is much better than offline training workflow, where specifically where the data is kind of dynamically changing. Okay, so both these workflow can actually be done using the combination of TensorFlow.js and Node.js. But before going into too much details, on a very high level, this is how the layers of TensorFlow.js looks like. So previously, like who are kind of quite comfortable developing applications in TensorFlow, all of us might have used the Keras framework, right? So Keras is nothing but a high-level library or framework on top of the actual lower-level TensorFlow operation. Although with TensorFlow 2.0, Keras and TensorFlow has actually merged pretty well, but still in some cases, we do go for the core Keras framework. But the idea is it kind of exposes certain APIs which can directly interact with the lower level, the modules in of your TensorFlow. Now, in this case, in TensorFlow.js, we see that the same kind of flavor is actually provided over here. The layers are kind of similar. Like you can still use the similar kind of Keras upper level or the higher level layers, and then like typically we have the core TensorFlow layers, but the main part kind of goes in the backend part where the backend computational engine, if it is run on a browser-based client device, then it kind of uses something called WebGL and kind of is used to train the models and perform the real-time inference. But apart from that, we talked about Node.js as an engine, right? So the Node.js also exposes a similar kind of an server, which can be done or maybe deployed at a local level system, and it uses the computational power from that. Okay, so this is quite interesting, and the main feature I like over here is the same kind of flavor which TensorFlow.js tries to provide, which is quite consistent with the original TensorFlow framework. And even some of the pre-trained models from TensorFlow can actually be converted or deployed using the same flow. Okay. Now, before I can go into too much details, let's see a fun video, and we'll talk about it later, but let's see from it first. And these are some of the demos which are actually available in the TensorFlow official website, TensorFlow.js official website, and there are multiple demos like this. But this is something which I actually like, and I'm sure like all of you might have played this same game before. Okay, so we'll take some time to observe this, and then I'll talk about like why I'm kind of showing this and what is the kind of beauty of the entire TensorFlow.js framework. Okay. So we see that our packpan agent is kind of moving. And we also see that whatever that is happening over here is actually quite real time. Okay. All right. So again, the purpose of showing this video is not to showcase my Pac-Man playing skills, which definitely requires some work to improve further. But the beauty that kind of comes out of it is the concept of transfer learning, which is beautifully embedded within the entire flow. So often, like some of us who have already worked on certain machine learning and deep learning workflows, we might have leveraged transfer learning to a great extent whenever the data sets that are available is quite limited, and when we kind of depend on pre-trained models on existing larger data set, and maybe we just fine tune on limited set of data for our use case. So that is essentially what transfer learning does, right? So this is an example of transfer learning where we saw that initially before starting the entire system, we just took few images, or just I think 2 samples from each of the steps or stages that we have. Then we kind of trained the model, and based on the transfer learning, we saw some loss function which is also generated. And once that is done, once we got the trained model, we actually did the playing and the deployment part in real time, and it was able to control the environmental agent. Okay, so that is another benefit of TensorFlow.js. It still has the same flavor of transfer learning and other such options that is available over here. And I would highly recommend all of you to try this the demos that are posted in the TensorFlow's official website, and it will be really fun to see like what are the other applications people have actually used it. Okay, so with this, I'll also actually show some examples from the actual TensorFlow site. Okay, so again, like for all the details, tutorials, the TensorFlow.js original site is actually the one of the best resources that we can get, and these are some of the fun demos that are available. And there are many, like people are actually coming up with their own demos, maybe publish the workflow in GitHub, and then they try to kind of connect this back to this particular tutorial site, and people kind of deploy it. And there would be like a lot of examples where Node.js will be used for multiple applications. So I'll highly recommend all of you to try this. Apart from that, there is a library called Node-RED, which is I think developed by IBM on top of Node.js, which has a good integration with TensorFlow.js. Okay, so it kind of provides you that how exactly the Node-RED package can be used for some of the machine learning or deep learning workflow through Node-RED. So typically Node-RED provides kind of a low code programming environment, and it kind of has that designer view where we can just connect certain building blocks together and complete one end-to-end machine learning workflow. So typically for people who have very less exposure to machine learning can actually leverage this framework very well. And this is one of the good examples where Node.js along with TensorFlow.js has been used to kind of complete some of the workflow. And this is quite popular even in the IoT world, where such a workflow can be easily deployed on edge devices like Raspberry Pi, Arduino, or BeagleBone. Okay, so I would highly recommend you all to kind of go through it in a little more details. It's quite fun actually. Okay. All right, and there are certain tutorials where how Node.js can be integrated in the entire workflow and be used along with TensorJS. So I won't go through it in much details, but I would also highly recommend all of you to go through it. Okay. Now, as I initially mentioned, that let's say I went for something like an offline model training flow where we initially, let's say, gather data from different sources. We train the model using our usual Keras or TensorFlow approach. And let's say once we have that trained model, then how exactly do we just do the deployment part on the edge devices so that the real-time operations can still be done. Okay, so this is one classic example where TensorFlow models, the core TensorFlow models, can also be converted into TensorFlow.js models. So this kind of gives the workflow. So we have something called TensorFlow.js converter, which actually converts a usual Keras or TensorFlow model into something called TensorFlow.js's graph and layers model, which is much more like optimized. And using that graph and and layers model, it can be actually well integrated to a JavaScript app. Okay, so basically this is very useful when we go for that offline training workflow or offline modeling workflow, where the training happens outside the real time or the production system. But once we have a trained model, similar kind of a conversion can be done to for the deployment part. Okay, now, as I said, we will be discussing about certain use cases which might give, more insights or more understanding that why exactly TensorFlow.js is required. So, as I said, for certain real-time anomaly detection, use cases, typically at the sensor level, at the edge level, it is very important. Now, typically at the sensor level, the data is not that high. I mean, in terms of size, it is not that large. It is just few numbers that can be captured from those sensors directly. But what is more important is the dynamic nature of the data changes. Say, for examples, based on certain environmental condition, the sensor might react in different ways, or maybe there is a natural loss or degradation of the sensor values itself. So basically the nature or the statistical property of the data itself is changing, right? So in such cases, going for an online modeling flow is very important. And that is where the model would need to be trained again and again based on the real time data that is flowing, and based on that it can be deployed for the final inference part. Otherwise, let's say if we went for something like an offline modeling flow in this case, and let's say because of the natural wear and tear of the sensor, or maybe because of certain dynamic environmental condition, the maybe the magnitude of values for that particular sensor is kind of changing. And when we train a model on a different data distribution or different, let's say, statistical property of a particular data or a data set, in that case the model efficiency, or let's say the accuracy that we use, can get like affected significantly. Okay, so that is one example where a real-time modeling scenario is important. Okay, so other such use cases is like, let's say if we want to forecast certain sensor values, and we want to have something like an alert mechanism where, based on the forecast, if it is beyond a certain threshold, we want to generate alerts, and send it back to the user. So these are typically quite useful in manufacturing use cases, typically in manufacturing shop floors where such auto failure detection is very important. And at the same time, this is one more example which kind of shows you your edge device performance using machine learning. So we'll even see that. Okay, let me share this. So this is again a website which is developed on top of Node.js and JavaScript. It's called Clinic.js Doctor, which is used for diagnosing certain sensor or device performance. It kind of gives you entire step by step that how exactly it can be done. And there are like a lot of good example which shows you real-time monitoring use cases which people have actually developed using JavaScript and TensorFlow.js. Okay, all right. And apart from that, the Node-RED is one of the use cases that we already discussed. And typically for IoT workflows, this drag and drop kind of a feature is very useful and very helpful. Okay. All right. So with this, we'll go to the next section, which is on TensorFlow Lite. So we talked about the benefit of doing machine learning at the client or the edge devices, but that is using JavaScript when we talked about in TensorFlow.js. But how exactly we can still leverage the same Python-based or that same the TensorFlow models and just do the deployment part on edge devices? Like, do we really need a client-based mechanism to do that, or Or let's say in case of let's say the TensorFlow.js, we had a particular server either which is implemented through Node.js or any other way which is running on the local system. But is that server also really necessary for doing that, right? So with TensorFlow Lite, it kind of removes that necessity, and the same, the TensorFlow related models can be further optimized and deployed on the local edge devices and achieve that level of performance that we want using some of the trained deep learning models. So TensorFlow Lite is actually an open source deep learning framework for on-device inference, particularly for on-device inference. And when I say on-device, it is not only applicable for some of the embedded devices like Raspberry Pi or NVIDIA Jetson or maybe Arduino, but even for mobile devices, TensorFlow Lite is very popular. Like typically, I know about it is quite useful for Android devices. I'm not sure about the iOS ones, but probably they have a flavor for that also. So TensorFlow Lite kind of works with a huge range of devices, from even the smaller microcontrollers or chips to powerful mobile phones. But typically, it has two main components. So one is the converter part, which kind of converts a usually trained TensorFlow model into something like a light format. So when we talk about a light format, it is further optimized, and the optimization typically happens at the floating point level, where I think typically for a TensorFlow model, it uses a floating point, I think a 32-bit kind of precision level. But when we talk about TensorFlow Lite, it kind of goes as low as an int16 kind of a optimization level. Okay, so basically the models are much more optimized, much more lighter, both in terms of size and in terms of weight. So the computational operations that happen underlying the model is quite minimum and much lesser than a usual TensorFlow model. Okay, so basically these are lightweight TensorFlow models which can be deployed in your edge devices. Now coming to the interpreter part, so let's say if we have an optimized model, how exactly do we run those optimized models? So for running those optimized model, we have the interpreter part, which kind of converts those model and makes it efficient to run on embedded devices like let's say Raspberry Pi. Okay, so again, like bringing a reference to the offline and the online training flow. So usually TensorFlow Lite is used for that offline training module, where the model is trained using a lot of data on a different system apart from the edge device. And once the trained models are available, then it is kind of deployed back into the into your edge devices for any online inferencing or online deployment related use cases. Okay, so how exactly does it work, right? So as I said, like it picks up any particular model which is trained on, or maybe we can retrain an existing model also. And when we will be talking about TensorFlow Hub, some of these models can actually be obtained directly from TF Hub. So instead of training our own, we can just get those model, retrain that on our use cases, and follow the same flow. Okay, and then the usual TensorFlow model is further compressed, as I said, so that like both in terms of the memory and the computational operation gets squeezed to a great extent, but yet the key weights and features of the model is preserved, so that it doesn't affect the final end performance that we want. Okay, and once the conversion or the compression happens, then we go for the deployment part, where we kind of take a compressed model and load that into a mobile or an embedded device and do the real-time inferencing part. And when we talk about optimization, as I said, it kind of follows this quantization property, which converts a 32-bit floating numbers into much more efficient and less computationally expensive 8-bit integers. So 8-bit I think is one option, but along with 8-bit, I think it also allows you 16-bit integer operations. And finally, it can run on a GPU. So one challenge that we might have always face whenever we work for deep learning workflow is availability of a GPU. And even if we have a lot of data, in most of the cases, although getting the data itself is a major bottleneck, but let's say if we have a lot of data, but if we don't have that the environment's capability or that compute power to handle so much of data and train a much more complex model, then even that itself is a challenge. And I'm sure like me, most of you might have faced something like a memory exhaustion error or a resource exhaustion error, which typically happens when you have a lot of data, and let's say when you get a higher batch size and then try to train a model, but unfortunately the compute resource that you're using might not have that much of capability to handle so much of data, right? So that is one typical use case where we go for the technique of quantization, which kind of optimizes the model, and it allows us to work on low compute resources. So even if we have, let's say, a GPU with a smaller compute power, then some of these models can actually run quite quickly. Okay, so that is kind of the benefit the entire concept of quantization provides. And TensorFlow Lite kind of implements quantization to a great extent so that it can be deployed directly into edge devices. Okay, so we'll also see a fun video which showcase the real-time nature of TensorFlow Lite. And again, this is not my video; it is kind of available openly in YouTube. But just one point, like before, when TensorFlow Lite was not there, like typically I used to develop like core TensorFlow or Keras model and then deploy it on Raspberry Pi using lower model architectures, like something like MobileNet, which is kind of much more optimized than some of the computationally expensive deep learning architectures, like let's say InceptionNet or ResNet. But even then, uh, there used to be some kind of latency involved, and real-time inferencing was actually quite challenging, like typically in use cases which involved maybe taking a live video feed using a camera in Raspberry Pi, or maybe capturing live images and then applying those models on top of it. Maybe the workflow used to be successful, it used to run and produce the result, but the latency that was involved in it, it kind of did not bring that real time nature. It was not exactly real time. Okay, but when we see or when TensorFlow Lite became popular, we can see that the results that we get are actually like quite real time, and it kind of helps us to perform some of the complex operations with quite ease. Okay, so this is one use case which we'll be seeing right now. We see how real time it is able to do the object detection part. And the feed is coming through a camera which is attached to a Raspberry Pi board. Okay, so yeah, so this quick video actually shows that how beneficial TensorFlow Lite is, and how exactly we can run something on real. Now, this is one common question that I get in most of the sessions wherever I go for such discussions. So, what are the typical supported embedded device which supports TensorFlow Lite? So, these are some of the list of the devices which are mentioned in the official website of TensorFlow Lite. So, some of the the recent one like ESP devices, like I myself have worked on those low power Wi-Fi modules or ESP devices, and for like typically those are like very simple devices which has very minimum compute power, but yet something like TensorFlow Lite can actually be deployed on such devices, and some of the operations that we saw so far can be deployed in real time. Okay, so apart from the common ones like Raspberry Pi, Google Coral, Arduino, and some of the other microcontroller chips, ESP is one of the quite popular microcontrollers which are kind of coming in and used for some of the real-time use cases for such IoT scenarios, can actually also be used for deploying some of those TensorFlow Lite models. Okay, so this kind of gives a good picture that how well supported TensorFlow Lite in such embedded devices. Okay. Typical use cases of TensorFlow Lite for IoT system, as I said, like whenever there is a real-time problem, TensorFlow Lite can be used quite efficiently. But the only thing is the model training needs to happen offline so that the only deployment happens on the real-time system. So for let's say real-time security camera or security systems where we want to do something like a real-time person recognition or maybe something like a threat detection using the cameras. So these things can be done quite efficiently using TensorFlow Lite, or even in traffic monitoring use cases. Or let's say if we want to deploy a system which can check whether a person is wearing a helmet while riding a motorbike, or maybe something like wearing seat belt while driving a car. So these kind of real-time monitoring use cases can very well be done using TensorFlow Lite on any IoT system or any edge devices. And apart from that, one common problem that people uh, kind of trying to solve right now is on indoor navigation system. So some of you might already know that GPS actually doesn't work when we go for an indoor navigation system, and people usually depend on certain reinforcement learning algorithms or certain robotic path planning algorithms to do the navigation system for indoor systems on real time. So this is one good use case where TensorFlow Lite have actually been used by many people to do some such kind of navigation work in an indoor environment where something like GPS actually doesn't work. Okay, so these are some of the prominent use cases, but it is not just limited to it, but these are just some examples that I've shown. Okay, all right. Now coming to the next section, we are going to discuss about TensorFlow Hub. As I said, TensorFlow Hub is kind of a repository where people can actually make their own trained models as public so that it can be reused for multiple use cases and scenarios. So consider this more or less like a GitHub where we kind of post our code and make it open source for other public to use, right? So this is kind of a GitHub for trained TensorFlow models. So here in TensorFlow Hub, many people have actually published their models and made it open source, and people can actually download those models and just do the deployment. Like basically there are certain modules or frameworks which is available in Python, using which we can connect to a remotely deployed model, and the same remotely deployed model can be downloaded on those, let's say, the local systems or local devices, and the real-time inferencing can actually be done. Okay, now, this is another way which allows machine learning and deep learning to be quite scalable and portable, which is one key aspect. So let's say whenever we go for that offline training mode where we have trained our models, then how exactly do we kind of move the trained model into the local system? Is it like maybe take that particular file through certain file transfer system and just drop it in an edge device? But it might be possible, but when we talk about certain production level system, that may not be a good option, right? So there has to be a synchronized way, something like a CI/CD pipeline through which a trained model can be pushed to a particular hub or repository, and then as and when a new version of the model is available, it can be pulled back into the edge device, and using that model, the remaining part of the deployment cycle or the inference part remains as it is. So this TensorFlow hub actually makes such model or the workflow quite scalable and makes those model portable, so that whenever a particular model is published into the TF hub repository, the version gets updated, and based on the latest version, we can actually pull in the latest model and then like run that or do the inference part from the local device. Okay, so TF hub actually kind of is a library that allows us to download or reuse whatever the latest model versions that we get with like minimum amount of code. Like there are like a lot of high level APIs that kind of helps us to do it with minimum amount of code. But the only beauty over there is like in some cases we might not have the data required to train for a particular use case, right? But let's say if someone who has that data, who has prepared those large and well trained models, can actually publish that. And for someone who just wants to do the inference part or maybe just the deployment part in real time, they can actually take those models and do just the deployment part. It kind of, so basically TFF kind of uh, ensures or enables that option of sharing trained models and deploying those to the final edge or IoT device. Okay. So why TensorFlow Hub again? As I said, it is quite easy to kind of discover some of the latest state-of-the-art trained models, which otherwise, if we would have to, do the training part for, like, let's say from scratch from our part, first of all, like it can be computationally quite expensive. It can take a lot of time to do that, and at the same time, in spite of, let's say, we have the data and the compute resources, sometimes some of these deep learning models requires quite heavy hyperparameter tuning to get the best result. And if we are not able to get that hyperparameter tuning right, we might not get the best result. But TensorFlow Hub actually kind of gives us an option that if someone has actually been able to tune the model to the best possible state, and then once it is trained and made publicly available, we can actually reuse some of those openly available models. Okay, and it has, like as I said, like good high level APIs, which ensures the usability part of it. Like it's quite easy to use and integrate that to the existing code, and it ensures that the models are actually portable. So basically, the models are not dependent on any local or let's say a remote cloud server, but it is kind of available in a very seamless way. Okay, and it kind of supports a wide range of platforms, and it has models related to TensorFlow.js, TensorFlow Lite, Google Coral related models, and even based on certain use cases, which we'll be seeing from the actual site again. Okay, and it ensures that loading a particular trained model is quite seamless, which is important for an an offline uh, you know uh, offline modeling flow, especially on an embedded device. So it kind of ensures that it is seamless, and the remaining part of the deployment part on the inference cycle kind of remains as it is. Like we kind of just pull in the best version of the model from the online repository. Okay. So before going to the summary, let's take a look at uh, the official websites of TensorFlow Lite and TensorFlow Hub, which will kind of give us a good understanding. And believe me, like whatever the documentations that are available would be probably, I would say, it's the best from the official websites itself, so that we don't need to go into other sources for learning it or to know more about it. Right? It gives you like a lot of good examples. And in fact, like I was not sure whether it will be applicable for iOS also. Right now, I can see that it is clearly applicable for iOS apps as well, not only Android. So TensorFlow Hub kind of gives you those examples, like how it can be used. And at the same time, there are some good tutorials available for not only image classification, object detection, and some of the more state of the art methods like question answering. Okay, so there are like a lot of such options which are available, and I would highly recommend all of you to go through it. And next we would see the TensorFlow Hub one. So basically, this is where how the the TensorFlow Hub official website looks like. And as I said, with minimum code, we can actually load the trained models. And let's see if I can show the guide part. So it kind of gives you like quite a good amount of step-by-step way how the pre-trained models can actually be used. And installing it is also quite easy. Like using the simple pip packager, we can actually do it. And apart from that, it has good options on different frameworks or different formats through which we can actually get it. Okay. So yeah, so I would kind of highly suggest all of you to go through it, not only the tutorials but also the trained models. And it kind of articulates all the different models in a very good way, like based on the problem domains, based on the model frameworks, or based on some of the use cases. And we can also see the list of the publishers who have actually published it. Okay, so it's quite beneficial when we talk about scaling up a particular deep learning or machine learning workflow, particularly for edge devices. All right. So with this, we come towards the end of the session. But before ending, I just wanted to summarize this concept of online machine learning, deep learning flow on edge devices and versus the offline one. So typically on the online part, as we had discussed, the data is kind of dynamically changing, and whenever we get dynamically flowing data from such sensors or edge devices, we can go for something like TensorFlow.js with Node.js, which can be very much used for getting the real time or the live data, then train that based on the flowing data that we get, and at the same time do the real time inferencing part very quickly. So that's where like TensorFlow.js and Node.js is very helpful. Like typically, if we want to deploy machine learning and deep learning models at edge or client devices, this is quite useful. And apart from that, we talked about the offline training part, basically the offline modeling flow, where the training is done offline, but the inference can still be done on an online, on an edge device. So that is where TensorFlow Lite is very much useful, where the training happens on maybe a much more stronger, computationally expensive machine or a resource. And once the trained model is available, it can be converted to TensorFlow Lite model using that same quantization technique that we talked about, which optimizes the model further, and then the real-time inference can be done. And apart from that, we talked about TensorFlow Hub, using which certain pre-trained models can be obtained. And those pre-trained models can be of different formats, like it can be TensorFlow.js models, or maybe these are TensorFlow Lite models, or maybe the usual TensorFlow models. But once those are obtained, that can be used to do the remaining the deployment or the inference part. Okay. So that's all for this session. And I know we discussed a lot of topics, and some of these are quite interesting. And maybe like since I did not go through the basics of it, but feel free to ask me any question and I'll try to answer. And even if you did not get to understand it, but don't worry, you can ask those questions right now, and I'll try to answer some of those questions. Okay. All right. I think we have few questions on the chat window. Let me try to open it. Okay, I'll try to go through it. First question: is it quite impossible to run in local time without having any cloud-based high-performance system for computation? So this is for the first question, that can we actually run certain models or do the modeling part on local devices without having any cloud-based high-performance system? So typically, it particularly depends on use cases. In certain cases, as we talked about, use cases in which the data is gathered from sensor devices, right? So in such a use case, the volume of the data is not much. Like even the size of the data is quite limited. But the main thing over there is the data is dynamically changing, maybe based on the environmental conditions, or maybe based on certain other configurations, the data is dynamically changing. So in that case, offline model flow is actually not recommended at all, and online model flow is required. And when we talk about online model flow, it would need to happen at that client device itself. So that is where local machine learning models are important. And we actually don't need any cloud-based high-performance system for computation in such cases, because typically the data is quite small, and for certain smaller use cases, running machine learning model is actually doesn't require that much of computational power. So mostly the computational powers or the need of GPUs comes when we mostly deal with unstructured data, like typically, let's say with images, or let's say with heavy text data. In such cases, maybe a higher compute power is required, or maybe something like GPU can actually make the training process much faster. But if we don't have any such dependency on the size or volume of the data, we can actually go for an online based local model deployment flow. Okay. All right. Second is, can you please explain in detail how is the data cleaning and standardization happens on the real-time data before the training? So it's kind of remains same. Like whenever we go for an offline model also, it needs to go through certain pre-processing, standardization or normalization steps. So even in this case, this the required set of normalization or standardizations are applied. But only thing is, like, since it is we are not taking the entire chunk of data altogether, right? It is just using the real-time flowing or stream of data, which is collected over, let's say, a time window or a period of time. And based on that, it is kind of passed in batches where the cleaning or pre-processing happens. And once the pre-process or the processed batch data is available, then the same training flow remains as it is. So whatever the data cleaning or standardization process that we do for a normal use case, it kind of remains the same when we talk about a real-time or a runtime data training process. Okay. The next question is, can we put together TensorFlow on ESP32? So yes, ESP32 is supported using TensorFlow Lite, and it can be TensorFlow Lite models can be deployed in ESP32. Okay. What is the optimization? Is the optimization configurable? So I think the optimization is configurable. Typically, I think I have seen options. So the default one is I think 8-bit integer level quantization, right? So I think it is configurable to 16-bit as well. But apart from that, there is a quantization or a optimization framework called TensorRT, which is I think developed by NVIDIA, which is quite popularly used for model optimization or quantization. So just in case if the optimization configurations are not available through the the core TF Lite module, but I'm sure like TensorRT does have that option. And typically we want to configure it to the lowest possible level, so the default parameters are actually available at that level. So I think that's why like in most cases people generally do not go for any specific configuration during the optimization step, but I think that is an available option over there. Okay, can you please share the presentation? Yeah, so the presentation I can share. After quantization, how are the models deployed on real-time IoT devices? So when the quantization happens, basically all we get is a compressed version of the model, and the same compressed version can actually be loaded onto the devices. Now typically people go for something like, as I said, like a CI/CD pipeline, or maybe through TensorFlow hub, using which as and when the quantized or the optimized version of the model is available, it is kind of directly pulled into the device, and using the deployment or the inference script, it can be used. Okay. So what are the constraints on offline models? Will they ever improve with time? Okay, so in offline models, sometimes people spend a lot of time in hyperparameter tuning, or maybe gathering more data, which is maybe available at a source which is away from the final production system, or maybe the final edge device, right? Or the IoT systems. So that's why people generally go for offline model flow. In terms of constraints, it typically depends on the data that is available and the compute power that is available for training. But other than that, I do not see any such constraints. But as I said, like if the data is dynamically changing, and the results are required in real-time use cases, in fast use cases, so that's where online training or online modeling flow is more important rather than offline modeling flow, because by the time you collect data from the sensors, from the real-time sensors, and then you train a model and again deploy the file and then put it back to the sensors, by that time maybe the nature of the data itself is changing. And if the data distribution is changing, or even the core statistical properties of the data is changing, then the model would need to be retuned on the new data. Otherwise, the performance might not be as good as that. Okay. So I would say like those are the primary constraints. And the next question is, what other frameworks are available in the market? As far as I know, I'm mostly aware of the TensorFlow technology stack, but I have often heard about TinyML, which people are using in certain microcontrollers. So I would say that is another framework which is kind of quite popular. And I think even PyTorch is trying to come up with certain light models which can be used in such real-time and edge devices. And I think there are certain offerings from Apple also for some of the machine learning or deep learning workflows that are done in iOS or Apple devices on the edge. Okay, so I think those are other popular frameworks which are available. Okay, all right, thank you that you liked it. Any more question? I think we still have 4 minutes. And I hope like all of you got some insights out of the session. And if not, again, feel free to reach out to me in LinkedIn, or if you have any further questions, feel free to drop an email to me in my email site. Okay, or otherwise, like you can follow some of the other works that I do from my website itself. Okay. All right. I'll maybe wait for 1 more minute, and if no questions, we'll probably end the session. Sure, I'll share the presentation. Sure. Okay, I think we don't have any questions. So thank you everyone for joining this session. And as I said, hope this was useful, and feel free to reach out to me anytime for any further question. And stay safe and take care. Okay, bye-bye. Bye.